I'm going to start by introducing the concept of momentum. And momentum is, if I define it, and I'll give you a definition, but when I give a definition for something like this, it never shows up on the test. I know you guys write it down word for word and all that, but remember, it's never hardly a can you recognize the definition of a word on my test? Have you noticed that? So your notes often serve your old classes, not your new classes. But I like to think of momentum as inertia while moving. This is not a definition you will see in a book. But momentum is another way of measuring the inertia of an object. That's what it really is. It's another way of measuring the inertia of an object. I use this example, and I don't use it lightly anymore, but it's a good example. So if I have a bullet sitting on my desk, just a raw piece of lead, that's like 20, 30 grams. Picking it up, tossing it around, no big deal. It doesn't have that much inertia. But fired from a gun, it has an incredible amount of inertia. If you remember the definition of inertia, it's how difficult it is to change that object's motion. That's the definition of inertia. It's the object's resistance to changes in motion. So if the object isn't moving very much, it's easy to change its motion. But the more an object moves, the more difficult it becomes to change that object's motion. That measurement is called momentum, or that physical property is called momentum. So, and there's lots of use of that word. Who's heard of the phrase institutional momentum? Oh, that's not a good, I guess that won't be a good adjective to use then. Institutional momentum describes the fact that often a group of people have become institutionalized and they resist change. Look at this classroom. This classroom is the response to institutional momentum. We pack a class with a lot of students, put them in rows, and teach them. That's institutionalized momentum. Is it the best way to do it? No, but when there's 33 kids in the room, it's difficult to find other ways to do it. Does that make sense? It's called institutionalized momentum. We've been doing it this way for so long, we are resistant to change. So momentum in its usage is about resisting changes. And momentum is just another way of expressing that. Now, we use a lowercase p for momentum because that makes sense, of course. I'm sure you guys all understand why. No, we don't understand why. I don't know why it's lowercase p. I don't. Nobody knows. But it's the product of mass and velocity. Now, a couple of little tiny things here. Momentum is a vector quantity. So as it looks really clear, the bar is up there on top of the P to indicate its direction. It takes its direction from the velocity. Pretty straightforward. And the mass in this case is a scalar. It scales the value of the momentum. I want you to understand, though, measuring an object's momentum isn't the product of mass and velocity. I know we can calculate its momentum this way, but that's not what it's about. I want you to think about a rocket. A rocket's momentum is constantly changing because it's burning through its fuel. Its mass is going to change dramatically from the point it takes off to the point where it's in orbit. That object's momentum is also changing, but it has a changing velocity and a changing mass. But it has a momentum the entire time. So momentum is more than just this product. But one way to calculate momentum is by multiplying these two things together. There are other ways to measure momentum. In the same way that there's other ways to measure mass. We measure it by what it does. We can measure momentum by what it does. Its unit, though, is kilograms meters per second. It has no special name. But in a list of different ways in which we've seen kilograms meters per second, you understand that it can easily become buried in all the different things that we've already seen for the units that we have so far. And we have units yet to go. Everything is always some combination of these three. Three of these have names: Newton, Joule, Watt, right? All those have names, but there's been no specific name assigned for momentum. So it's just kilograms meters per second. So when you're asked to calculate it, you have to put a unit next to it. Make sure you do, but also make sure that you put after this the direction. Because remember, when you answer a question that deals with momentum, you're often having to provide vector information, and direction is going to be a part of that. All right. Can I keep going? I want to derive something for you. I will not expect you to derive this yourself, but I want to derive something for you, okay? It's not much, just a little bit of algebra, but it's all right. Did you need to see it again?
Yeah, I don't know how it works.
It's all right. Doesn't bother me at all. Having to wait for it to sync. It's going to take a second. All right. So I want to start by looking at Newton's second law for a minute. Momentum on its own is just a value. It's just a measurement. It's like saying, here's velocity. This is what it is. We're going to talk about what momentum is about. So to talk about what momentum is about, we have to start here. And I want to bring two things together for this conversation. The first is a reminder that Newton's second law is about changing something about the object. Remember, it's about causing an acceleration, which is a change. Now, acceleration appears in a lot of places in our kinematics equations. But for the time being, I want to focus on just this one. And a reminder that we could rewrite it. All good? So I'm going to do a quick substitution. Everybody following okay? Just doing simple math. I'm going to be nice. I'm going to do this in steps that I think are super baby steps, with the hope being that no one has to ask, well, why'd you do that? So is that an okay baby step? So yet another baby step. All good so far? Still good? Lots of baby steps. All right, so simple derivation. I started with Newton's second law. I chose a kinematics equation, and I just applied the definition of momentum, and I produced this. Everybody follow okay? This has a name, and it's kind of important in this unit. We call this impulse. Both sides of this is known as impulse. An impulse is the method to change something's momentum. Impulse is the method to change something's momentum. You'll remember we had something similar earlier this year. We had something called the work energy theorem. And we talked about how the work done on an object was a method to change something's kinetic energy. Do you guys remember that conversation? These two things are very similar. Generally, there's differences, but these work in concert. They work together. One of the major differences is that kinetic energy is a scalar, but impulse is a vector. Next, impulse, like the work energy theorem, has an effect side, something that happened, and a cause side, something that occurred to make this change. It's in a cause and effect. Impulse refers to either side. So if you apply a force for a period of time, you are applying an impulse. And if object's momentum changed, then the object experienced an impulse. Do you see how I'm using the language okay? Again, so if you push on something for a small period of time, you are applying an impulse. You are causing an impulse. And if you observe an object whose momentum changes, then it experienced an impulse. The units on both sides will still be kilograms, meters per second. If you look at the other side here, that's going to be a Newton times a second. But a Newton is a kilogram meter per second squared times a second. We can cancel out one of those seconds and we get kilograms meters per second. They are the same unit. Please listen close. Newton second is also a unit of momentum. It has to be because it corresponds with kilograms meters per second. So they could, if they were writing a test question in an attempt to confuse you or to see if you know that both of these are different ways of expressing the same unit, they could say that the object's momentum is 5 Newton seconds, which will feel weird because it doesn't seem like it has kilograms and meters per second in it. Does everyone understand? So a Newton second is the same as a kilogram meter per second. They're the same unit. So put that in your notes, make it clear, put a little box around it. If they give you something in Newton seconds, they're giving you something that is a unit of momentum. So if we look at these two circumstances, the cups both striking the floor at the same speed, and then both cups being brought to rest, but just one happens to be on carpet and one on tile. Which cup experienced a greater impulse? Be careful, I'm intentionally trying to trick you. Think about it. Maybe talk with each other a minute. I'm trying to trick you. All right. Who says carpet? Who says tile? Who says neither? Trying to trick you. Change in momentum equals mv final minus mv initial. Both were brought to rest, so this was the same for both cups. Both hit the floor at the same speed. This was the same for both cups. So both cups experienced the same impulse, right? Now, I'm actually not trying to trick you. I'm saying impulse isn't force. Impulse is about the change in momentum. It's caused by force. But what this should tell you is something important. Why didn't the cup that hit the carpet break? How would you describe the carpet? David's got his hand up a lot today. But let's hear from somebody else. You've been great. Go ahead.
Soft.
How many of you would describe the carpet as being soft? And the tile is hard? What we think of as softness and hardness is something that you have a certain intellectual experience about, right? But physically, the difference here is that it takes longer for the cup to stop, right? It reaches the carpet and the carpet squishes. And that increases the length of time it takes for the cup to be stopped by the carpet. On the other hand, is the tile particularly squishy? No. So the amount of time of contact between the cup and the tile is much less. since they both have to experience the same change in momentum, if it does so with less time, that means it's more force. And if it does so over more time, it means less force. Who's been fortunate enough to have to deal with a stupid water balloon toss or egg toss thing, right? Do you guys know what I'm talking about? You and some other child have been probably subjected to this little activity for the, I guess, amusement of your parental overlords. And they have rows of them, and one of you is given an egg, and the other one is told to stand over there, and you toss the egg to them. You guys know what I'm talking about? And then after all the eggs have been tossed, everybody takes a step back, and we repeat this process until last man standing. That sound like what a water balloon or an egg toss is? How do you catch that water balloon? Do you just stand there like this stoically and let it hit you in the hand? No, you don't, right? You do one of those, right? Because you want to increase how long it takes to stop. If you do so, that lowers how much force is on the egg or the balloon. Force breaks things. So if you want to change the force, you have to increase the time. In the case where you're trying to change something's momentum. I tend to try and talk about car accidents a little bit here because it's a good place to talk about it. And it's similar here. If you're in a car accident at 30 miles an hour, you're going to be brought to rest, right? You are a part of the car system. And so if the car is brought to rest, the hope is you will be brought to rest. I can think of only 4 ways you can be brought to rest inside your car. Right? Can you probably name them off? Dashboard, seatbelt, airbag. I would probably lump the windshield in with the dashboard if you're okay with that, because you can also be thrown from the car and stopped by something outside the vehicle. Now, you could probably name a number of other ways to get stopped, but the 3 that I want to focus on is the pillowy softness of the dashboard and the pillowy softness of your seatbelt and how much it stretches and how stretchy it is. And of course, the explosive impact of the airbag. But if you understand why these features work the way they do, you're going to be stopped either way. So you can be stopped by how long it takes the dashboard to stop you. You know, dashboards used to just be a steel plate in front of you. I mean, we didn't have plastics until the mid-50s and early 60s. So there's no synthetic that they could use to make it squishy. We didn't start to get that until the 60s in cars. So we, of course, made them. And I'm sure if you go to your car and you squish the dashboard, I'm sure it is just pillowy soft. Have you ever tried to pull a seatbelt to see how much it stretches? Does it stretch very much? No. But it can stretch up to 2-3 inches during a car accident, which is why they're supposed to be replaced after a car accident, because they no longer have their elasticity. You don't know that until you've been in a violent car accident and you've hit the seatbelt hard. Now, an airbag explodes in front of you. It has to be in place to be useful for you to push the air out. A dashboard stops you in milliseconds. A seatbelt stops you in tens of milliseconds. And an airbag can stop you in hundreds of milliseconds. Do you understand the power of that? Because each one is a power of 10. So when we went from a dashboard to a seatbelt, the effective force on the human being was divided by 10, which made what used to be a fatal accident at 30 miles an hour survivable and increased the survivability rate to a higher speed. And when we did it again with airbags, we've now made 70-mile-an-hour collisions routinely survivable, not without injury, but survivable. And we've made 30-mile-an-hour accidents, so you just get out of the car and walk away. That didn't used to be the case. So when we're talking about impulse, we're specifically talking about the application of force over a period of time. In addition to that, we're talking about how that will change something's momentum. I am not a sports person. I am coming to grips that I will appreciate sports under certain circumstances. And I like watching games, don't get me wrong. I don't take the time out of my day to follow a sports team. Does that make sense? But I can enjoy football. I can enjoy basketball. I tolerate baseball. And I don't mean that for you guys who love baseball, that I don't like baseball. I like watching people I know play baseball, but going to a baseball match, I'm glad they brought the timer now for the pitcher. I am glad. That has sped the game up and has made it more exciting. But you don't know this, but a while ago when I was younger, they brought players in front of Congress to drill them on all the drugs they were taking because they were roiding up. But I'll tell you what, the game was way exciting because there is home runs every inning, and it was exciting. I'll take that. I'll be honest with you. We're going to watch sports. I want it to be exciting. I know that that's not the point. The point is supposed to be a test of body, will, and all the orchestrated stuff. But look, they're all good players. When a ball gets into play, there's very seldom an error. They know what to do. They know where to throw it. That's why it's fun to watch Little League because they're going everywhere. But I digress. When they made them stop taking the roids, suddenly all of the home runs stopped, and the game was far less exciting and less viewed by people. So you're a baseball player, and you wish to hit the ball farther, and you work out all the time. Well, you can only work out so much and get so strong before you've reached the limit of what your body can take. So you're finding that you're not hitting the ball as far as you'd like. What could you do to hit the ball further? Well, you could change stuff. All right? You're hitting the ball as hard as you can. You can't change this part of the equation. Right? You have applied as much force as you possibly can. But you want to change this side of the equation. Well, that leaves one variable to change. So you drill a hole through the middle of your bat, taking the hardwood out of the bat, and then you roll up cork around a core of steel, and you fill that area with the steel core and the cork. Why? Because you need the bat to have the same balance point, and you need the bat to have the same mass that's printed on the outside of the bat because they get inspected. So you carefully cut that cap off, preserve it, and when you put it back on, you carefully make sure the wood grain and everything matches up because it's going to be inspected. But now, your bat weighs the same but is a little softer, right? What does that do? It stays in contact with the ball a little longer. What's the result? Your ball goes a little farther. So, bat boy, give me my lucky bat. I can't get myself any stronger, but I want to hit the ball farther. See how this goes? Right. Generally, we use impulse to describe things that happen fast. Generally, that's what we use impulse to describe. We can describe things that happen slow using impulse, but we generally describe things like this, things that have impacts, collisions, ball being hit by a bat, ball being hit by a racket, golf club hitting a golf ball. We tend to use impulse in those circumstances, and it tends to be where it gets used. But we can still make the comparison that there's something about kinetic energy and momentum that are similar. I don't want you to confuse them because they're not the same, and different things can be expressed. But let's talk about some examples in which these two things are the same and which these two things are different. Are we okay with that? Consider a bat being struck by, say, a force. I want to make it simple. I don't want to make it anything particular, but maybe I have an object going this way at some velocity. And it gets hit by a small force this way that causes its velocity to be reduced. Would this be a change in momentum? I'm not trying to trick you this time. I mean, did the velocity change? If the velocity changed, the momentum changed. That's simple. Did the speed change? I'm using this word differently here. I want to be careful. Did the speed of the ball change? Yeah, it's less, right? Because remember, kinetic energy isn't about direction. Kinetic energy is about speed, not velocity. Right? It's not about direction because we square the velocity when we calculate kinetic energy. Remember, it's 1/2 mv squared minus 1/2 mv naught squared. That's how we calculate kinetic energy or changes in kinetic energy. So in this circumstance, the ball being, experiencing a force and slowing down. In this circumstance, there was an impulse and work was done. Right? Because in both cases, the momentum and the kinetic energy changed. Now look, I'm trying to get somewhere. I know this is sounding simple, so let's talk about, say, a case where I apply more force. So instead of the force we just saw there, I apply a lot more force. And the ball returns in the other direction with the same velocity. So a ball is pitched towards the batter at 50 miles an hour, and the batter returns the ball at 50 miles an hour. Was there an impulse? Was there a change in velocity of the ball? Now, this is where I'm getting, you understand what your multiple choice is going to look like now? Okay. There was a change in velocity. Velocity is about direction, and the ball's direction changed. You see what I'm saying? There was no work done because the ball's energy didn't change. It has the same kinetic energy leaving the bat as arriving at the bat. So in this case, no work was done, but an impulse was imparted to the ball. Do you see what I mean? Now, I'm showing you different cases because I want to make sure you see where this is going. Is this a possible case where something could act on the ball to cause it to change its direction only, but not change its speed? Sure, we talked about it in uniform circular motion. In that case, there's a force acting all the time. That force isn't doing work, right? No work is being done because the object's speed is staying the same. But there's an impulse being provided all the time to change the direction of the ball. Interestingly enough, and this is where I'm really getting to the point here, the force has to be in this direction to cause this particular change. Do you see why? There has to be a force that causes the ball's velocity to stop in the X direction and start in the Y direction. A lot of people think I would just have to push on the ball upwards to get this to happen. But if I don't stop it moving to the right, it can't just be going up. It would be going up and to the right. So here's the last thing I want to point out. The direction of impulse is in the direction of the force. In the case of this problem, the ball had a direction to the right and then had a direction upwards. Right? You guys see the picture there? The impulse was never to the right and the impulse was never upwards. The impulse was upwards and to the left. That was the direction of the impulse. The impulse was never directed to the right and never directed upwards. It was directed this way. So impulse has a different direction than the momentum of the object. When you're asked about the direction of impulse, it is in the direction of the force. All right. That's probably enough for today. I think we've reached our limit of things to talk about. So we'll stop there.